Hello, this is Taylor SIFT. I'm Kevin Urrutia.
I'm Ana Cardenas.
So the SIFT features algorithm is named Scale Invariant Feature Transform. The purpose of this algorithm is to create different features within an image that you can cross compare to other images to see if the same object is present within another image. To do this, for example, this truck here, this truck has different features corresponding to these. These are generated into a feature space here, and you compare these features onto this different image of the same truck, and then the algorithm takes these different features, cross compares them, and then says if they're the same feature in this feature space, then that means it's the same object in both images. This is important for different robot localization algorithms. One of them being SLAM. You have to have different landmarks within your SLAM algorithm. And one way to create distinct landmarks is through SIFT features. You take a computer vision algorithm, you generate the SIFT feature for the landmark, and as you make your map or localize your robot, then that means that it's already been to these different landmarks and you can do your SLAM algorithm based on that. The first step in the scaled space is to generate, or in the algorithm is to generate the scaled space. This is done by taking the original image, blurring it consecutively, and then taking the same image, scaling it down by half, and then blurring it consecutively. This is done 4 different times. Based on the original 2004 paper, the best way to do this is through 4 different octaves, meaning 4 different times where we scale down the image and then blur it. The actual way that we do this in the code is through the Gaussian blur on the GPU. We take a kernel 5x5 generated on the CPU. This kernel is a Gaussian function with a standard deviation of 0.8. Basically, we do the convolution at each pixel location with the kernel. So we place the center of the kernel at a pixel location. We add up we multiply the different kernel elements with the corresponding pixel value. We add them up and then place them back into the center of the pixel, or the center pixel, and return the new image as a blur. Next is the scale down.
So we do the scale down function on the GPU as well. And what we did for this function was we simply scale down the image by 1/2 and we move each corresponding pixel to the corresponding halved location. And as was said previously, we do this for each octave.
So the next step in the algorithm is to generate the og space. So before that, these are the different scaled spaces. This is the 3rd octave. As you can see, it's getting more and more blurred as we go down. The final 4th octave is barely visible at the end of this part of the algorithm. So then, like I was mentioning, the next part is the difference of Gaussian.
So for difference of Gaussian, we take the blurred images that were generated in the previous step and we subtract them from each other. So how we did this on the GPU was we simply take the images, the blurred images, and do element-wise subtraction, subtract them from each other, and then this is what we get. So from the 4 different blurred images, we get 3 images for each octave. And these are the results.
Great. So then the next step in the algorithm is to generate these full key points. So as you can see, these key points are what is going to be used in the SIFT features to guess or to determine if these are the same objects within different images. So the majority of our key points in the results is around the mouth of the first pumpkin, the reflection of the first pumpkin, and around the eyes of the second pumpkin. So to actually generate these key points, we did this on the CPU. So basically, we want to take each difference of Gaussian space, compare those 3 images with each other. So we take each a pixel within the middle image of the difference of Gaussian, create a 5x5 neighbor region, and compare that neighbor region across all three difference of Gaussian images. And from there, you want to make 26 different comparisons to get a single key point. So basically, when you do these different comparisons, you want to keep the minima and maxima of the difference of Gaussian, because this is the derivative of the Gaussian. So that means that you're taking the derivative of the intensity value. So you're basically saving the derivative of the intensity as your key point. So you want to have your derivative be a minimum or maximum, or so that it's anything but a saddle point. So that is our generation of the key points. The next step is to reduce the key points to make them more robust. As you can see in our algorithm, that means that we reduced some key points around the mouth of the first pumpkin, this region here, and around the edges of this pumpkin. This is done through the GPU, where we basically take each key point that was generated in the previous step, map the neighbors of each of those key points, and then generate and then get the compare the different key points and their neighbors with their gradient values. So if the key point is something that we want to keep, it's a corner. So what does that mean? It means that the different gradients are all different compared to the single pixel location that is the key point. If they're not all different, that means that we're at an edge or at a flat point, and that's something that we don't want because it's not invariant to different things. So we want a corner. So that's how we reduce the key points here. Next is to do the histogram.
So what we did next was we created a histogram from the different key points that were generated. And this is right here. So we created a histogram going from 0 to 360 degrees with 36 bins to show the different orientation assignments of the key points. And as you can see here, we did an atomic add where we divide the position by 10 in order to get 36 different bins for our histogram. And then this is the resulting histogram that we obtained from the key points.
So the final step in this algorithm is to take this orientation assignment, the key points, and then create a feature vector that can be cross-compared to different images to see if it's the same object within different images. Then we, at the very end of this, we did a CPU comparison. We took OpenCV's implementation of SIFT features and called their function, and this is the output. So basically, I would say that our algorithm is comparable because we have the same kind of features. We have it around this reflection around the eyes and the mouth of both pumpkins. The only difference is that the key points generated by OpenCV are more robust and there are less of them because OpenCV used a different way to reduce the amount of key points. We used the Harris corner detector, so that means that it's less robust and it gets rid of less key points because there's a lot of edges here or corners. OpenCV used the Taylor series expansion across each key point and determined the Hessian of each key point, and then got a threshold value at each of those key points and was then able to reduce the amount of key points using that. And so they got less key points, but they're more robust.
Another noticeable difference was that our code was significantly slower than the one on OpenCV. That one only took a few seconds to run, while ours took about 20 seconds. And as Kevin mentioned, this is because we calculated the key points differently on the CPU.
All right, thank you.
Thank you.